Welcome to the Relaxation Times podcast. I'm Richard Hanzlik, product manager at Alpha Technologies, and today we're going to be talking to Unal Yilmazoglu about common failure modes in curing of prepreg materials. Welcome, Unal, and before we dive in, could you briefly tell us about your role as a senior scientist? What does that mean? And then what's the focus of your recent study?
Thank you very much, Rick. And happy to be here. This is Unal. I'm a senior scientist and applications team leader at Alpha Technologies. I specialize in the rheology of composites and polymeric materials such as rubber compounds, as well as the composites too. So the recent study that we have conducted is troubleshooting common prepreg failure modes using rheology, which is a really interesting and an important topic for composite manufacturers.
Excellent. Sounds very impressive. So I imagine prepreg manufacturing is a very complex procedure. What are some of the common failure modes that you've found are important, and why are they important?
Excellent question. Actually, temperature control, plus pressure control, and also the resin viscosity challenges, exothermic reactions are a big deal in the composite industry. So controlling them and beforehand, optimizing and troubleshooting them is a big research topic in the composite industry. So, for example, these failures can lead to weak spots, warping, as well as the ultimate composite failure when it comes to the production line. Mm-hmm. So basically, addressing them with the rheological methods gives a pathway for the design engineer, for example, to identify the early challenges and then early troubleshooting of the material before it goes to manufacturing. Okay.
So you said failures. In a practical sense, in a real-world application, what would a failure look like?
Great question. Would you like to get on a plane which has a void in the wings?
Probably not.
Probably not, yes. So it is the same, goes for the car parts too, car chassis, for example. So no one wants to drive a car having a void in the car chassis, right? For example, pressure, improper pressure control cause these type of voids. So it is a detrimental and then cause catastrophic failures for the actual parts in a composite.
Interesting. So you mentioned you identified these key factors. They were what? Temperature, pressure, and out time?
That is correct.
So could you walk us through each of those and what do those do? Especially the out time. I'm not 100% familiar with that one.
Definitely. Excellent question again. So basically we like to investigate the three pillars: temperature, out time, and then pressure. So for the pressure part, we systematically changed the pressure that is applied to the composite sample while testing, and then we got some results. As well as we changed the cure temperature for the prepregs, like I'm showing right up here. And then even we studied in a really narrow range. We have identified these slight variations or slight changes can cause drastic changes at the end of the product. I mean, the stiffness changes drastically. But when it comes to out time is basically manufacturing these or preparing this sample and leaving on the table like this for a long time. And then we systematically investigated how long we should keep these prepregs without having any performance failures.
Okay. So I took a peek at your paper before this, and one thing I noticed is typically the results that you obtained are performed on a DMA, dynamic mechanical analyzer, or a DSC, differential scanning calorimeter. And then I've also seen scientific rheometers. But you said that this was performed on an ESR, or encapsulated sample rheometer. What's the difference between that and the instruments I just listed?
Excellent question. ESR is a 3-in-1 instrument. Actually, it can be used as a DMA, DSC, as well as the scientific rheometer. But what makes ESR unique is, for example, to prepare the composite materials, DMA requires a special sample prep method, as well as it's labor-intensive and then time-consuming. Plus, DSC uses only milligrams of sample. It's not going to give you the whole movie of the sample. On the other hand, in the scientific rheometers, we're basically testing these materials in kind of plates. The scientific rheometers are open to environment, so it can cause some sort of slippage inside during the testing, which is detrimental of the study. So what makes ESR unique is it is easy to prepare sample. So all you need to do is get your Prepreg sheets. So I'm holding right now 0.4 millimeter of Unitape Prepreg sheets, and then cut these sheets with the cookie die cutter. We like to call it that name. And then stack on top of each other. And then
typically, how thick do you make that sample stack?
Great question. 4 to 4.5 millimeters thick. Okay. It's enough. It takes like 14 or 13 Prepreg layers, depending on the thickness.
And that's kind of in line with what a real world part would have, that sort of thickness, right?
Definitely. Okay. So instead of just testing only one layer, the typical parts consist of much more layers than only one layer. So this is a much more realistic definition, and also giving you the movie of what's going on within your composite material.
Okay. And then I see that that's a final sample right there. What's that orange ring around that?
Oh, definitely. Great question. And I'd like to add one thing before I answer the question is ESR compared to the scientific rheometer is totally enclosed. I mean, this has a closed boundary. So you make sure that your material does not slip inside the rheometer. So we get better data, the most accurate and reliable data with the test in ESR. So further increase the data requirements and also the data analysis, we encapsulate these material with our patented silicon O-ring. So it also adds another encapsulation. So we better make sure our data is accurate and repeatable.
Does that help the resin from flowing out of the prepreg during the heating stage?
Oh, definitely. Okay. Not only for prepregs, we use these silicone O-rings for resin-only studies too. You can test the resins without prepregs.
Okay, so you can do the carbon fiber with the resin or just the resin.
That's definitely.
Interesting. And then typically, what kind of torque range would you see on this? I know on scientific rheometers, you will max out around maybe 20 decilnewton meters. What do you see on an ESR?
In the ESR, our upper range is 240 decilewton meter, which means this uncured prepreg or uncooked prepreg is quite flexible. But when it cures, it looks like a glass and it's pretty stiff. So your rheometer needs to be capable of measuring high torque values or high stiffness values. So that's another great upper limit of the ESR that you can test really rigid and stiff materials.
Interesting. So it sounds like it's a little bit easier to use, and you were able to obtain the data from your study around the common failure modes. Let's get practical for a sense. In a real world application, what do the results of your study tell us?
Great question. For example, in the cure temperature studies, what we investigated, the cure temperatures from 122 degrees C to 132 degrees C with a small increments. And what we have identified is even these small changes in the temperature cause significant material property changes at the end of the cure. Your stiffness changes drastically. So with the ESR, you can optimize your cure temperature, for example, without going to without having a big parts like manufacturing big parts in an autoclave, because prepregs materials are really expensive, and making a big part just for the optimization study and put it in an autoclave and take it out and test it requires a lot of time and it is costly. So on top of that, we also identified the pressure. So interestingly, the higher pressure normally gives us the better at the end of cure properties. But the problem is what we identified, there is the sweet spot in the pressure range that gives you the desired composite material properties if you're aiming higher stiffness. And the most interesting one that we have found is the out time. So I remember you had some story with the other time, right?
Yes. So there's a friend of mine in the industry. I won't name names, but they work on the material inventory management for one of the U.S. military's weapon platforms, and he had something like 2,000 pounds of prepreg in a freezer. And something happened that their power went out over the weekend, and when they came in, that material had been unrefrigerated for 48 hours and technically out of specification. So they had to scrap however many hundreds of thousands, if not millions of dollars worth of material because it is out of spec. So what you're saying is he didn't necessarily have to throw that out.
Definitely. They can. It is easy. There's an easy test for the prepregs especially that in our study highlight that so normally this is the golden rule. If you leave these prepregs outside, basically you shouldn't use it, right? But what we have found out that up to 9 days of out time, again, out time means leaving these prepregs without intact, but it can, the moisture attack can be happening or resin chemistry can change, but up to 9 days, we don't lose any performance in the prepreg. But after the 9 days, perhaps some changes in resin chemistry causing the material failures, plus the moisture absorption getting more detrimental, cause some issues. But for a specific prepreg that we used, for 9 days, you're good to go. Don't need to.
And so would that time change from material to material?
Definitely. And then with using the ESR with a test, you can quickly identify without scrapping the whole expensive materials.
Okay, great. And then there was one more topic you covered in your paper that we haven't discussed, and that was layup orientation. You did something around putting the direction of the woven fibers at different orientations. What did you find there? What were your findings?
Definitely. In this study, we used a unitape prepreg layer. So right now I'm holding the unitape prepreg layer, which we can define this direction as 0 direction, and it's like the vertical direction. And what we have done is we take it out and then put these unitapes on top of each other within a specific direction. For example, if we want to get the 90 degree direction, we put in a orthogonal layup wise. For 0 degrees, we put on top of each other. Plus, for the 45 degree, we pick the angle for 45 degrees with the 45 degree increments. We get our coupons like that. Interestingly, we can get the fingerprint of these layup orientations from the ESR data. What does that mean is 0 degree, 45 degree, and 90 degree has unique peaks within an ESR. So you can use this for quick QC test and the product identification, whether it's a right angle that we put in a layup or not. So with the 45 degree angle, we get higher stiffness, by the way.
Interesting. Thank you for that. When most people think of alpha technologies, they think of rubber testing, but this is composites. What do you see for the future of alpha in terms of composites and maybe even plastics testing?
Great question again, Rick. So in the past, we also put a lot of effort to designing our ESR to make it more suitable for composite materials. So right now we have a quick sample prep method. It takes maybe the first time 5 to 10 minutes, but later on 2 to 3 minutes. And then testing, you only need to take this prepreg sample stack, like 4.5 millimeter, put it in a Rheometer plate, and then press the ready button. It's operator friendly. So what's the next is for us to design new test methods. For example, making the QC tests much more easier and quicker. So by doing that, the customers can get an understanding whether they should release the parts or they should take and then do some optimization or do some troubleshooting. On top of that, we are still designing and developing our instruments, make it more suitable for ultra high temperatures and ultra low temperatures too.
Thank you, Unal, for your time and your expertise.
Thank you very much, Rick. Happy to be here always.
I also want to thank you for listening. If you have any follow-up questions or would be interested in downloading the full research, please check out alpha-technologies.com, where you can find the full download.